Hello everyone, my name is Zhe Fu. I'm a final year Ph.D. candidate in transportation engineering at UC Berkeley. My research focuses on physics-informed learning and control for mixed autonomy systems. Today, I'm super grateful that H2H8 gave me this opportunity to showcase one line of my Ph.D. work, and I want to introduce how a few automated vehicles can smooth traffic for everyone. Have you ever been stuck in traffic, barely moving, then suddenly speeds up and then slows down again? It's really annoying, right? And on the left-hand side, I'm showing you the video captured on the highway, which is the phenomenon that I just described, the stop-and-go waves. And what makes it interesting is that usually this phenomenon is not caused by accidents, road closures, or bottleneck. On the right-hand side is a video captured from a ring experiment conducted in 2008 by a group of researchers in Japan. They deployed 20 vehicles, human-driven vehicles, on a ring road structure. And they showcased that without any bottleneck, just because of the human reaction and delay, the stop and go waves actually can emerge. Then, as a traffic engineer or a researcher, we will raise the question like, can we actually eliminate this stop and go wave phenomenon? And a group of researchers from Vanderbilt, Rutgers, Temple, and the University of Arizona, they actually shows that with just one autonomous vehicles, we can have the ability to eliminate these stop and go waves. They replicate the ring road experiments here, but replace one of the human-driven vehicles with a vehicle that we can control and deploy the specific speed on. In the video on the bottom, it showcases the speed profile for each of the vehicle. And the red curve indicates the speed that we deployed on the controlled autonomous vehicles. As you can see, before deploying any control, which is around before 100 seconds over there, the speed stop and go waves emerge and actually amplify over there. But after we deployed the control on top of that, it actually effectively influenced the following vehicles and shrink the speed profile. And this experiment showcased that with only one single vehicles, we can have the ability to eliminate stop and go wave, but it's still within a controlled ring settings. The natural question to raise here is, how about in the real world highway? Then for the highway, there are two sets of challenges. First of all, there is no longer the controlled environment, it's no longer just a simple ring road. It's a more complex infrastructure. And secondly is in terms of the control that we can deploy. For the automated vehicles, there are several different levels of challenge. First of all, in terms of the automation level, currently on our real world, most of them are not fully autonomous vehicles. They are at most achieve the adaptive cruise control level, which is level 2. And in terms of coordination level, even now, most of the vehicles are still human-driven and only a few automated vehicles are available. And what's even worse is, even for those automated vehicles, they're coming from different companies or different OEMs. So they have various sensing and acceleration abilities. So the research question we're trying to tackle here is, can we utilize this limited number of partially automated and heterogeneous vehicles to stabilize traffic conditions for all vehicles, not just those vehicles that we can control, within the highway real-world systems? And the answer is actually yes, and I will explain to you through this talk. For today's talk, I will firstly introduce the control strategies that I designed to tackle the previous research question. And the overall idea is I will deploy some control to design the smooth speed profile to deploy on the autonomous vehicles. And I validate the control strategy in simulation with the real traffic trajectories. And results showcase that with less than 4% autonomous vehicles penetration, we can achieve more than 15% energy saving for the whole system. Here, we use energy saving as the proxy to showcase the smoothness of the traffic systems. And later, I will introduce how we deploy the control strategy into the real-world experiment, which is the largest mixed autonomy traffic experiment to date, with 100 automated vehicles deployed on the I-24 highway during the morning rush. And in that experiment, we showcase with 100 partially automated vehicles, which is actually equivalent to less than 2% of automated vehicles penetration, we can achieve more than 10% measured system-wide energy savings. And in the end of the talk, I will try to summarize and give you a reflection in terms of the whole research framework design in terms of modeling layer, control layer, and the experimentation layer as a co-design loop. And as a spoiler alert here, just trying to give you a higher level sense of the whole project and the framework behind that is basically on the modeling layer, we are trying to capture the traffic state estimation to sense the downstream conditions so that we can deploy the control strategy on top of that to design some target speed and plan for a smooth speed profile. And with that speed profile, we deploy on top of the few automated vehicles, let the few automated vehicles as the lead control to execute the plan and shuffling the human drivers behind it. So let's begin the journey. But before I dive into the control strategy demonstrations, I want to give you a problem setup. So here is an illustration of a single lane ground transportation traffic here. And the red car represents the few automated vehicles that we have the ability to control. And the car right in front of the red car is the human-driven vehicle, but we have the ability to sense some information, for example, the location and the speed of the vehicle. And we call it the sensed human-driven vehicle that's marked as the blue car. And for the rest of the car are all white. They are the other human-driven vehicles that we don't have any information from. So this setting provides us some informations. For example, the macroscopic observations, and we call it local states, which compose of the eagle state, which is the car that we can control. We know the position and the speed of that, while along with the position and the speed in front of it, which is the lead state. And in some cases on the road, we might have some loop detectors or cameras or radar. Then for those roads, we can obtain some high-level information to indicate how congested of the road, and we call it the traffic state estimation. And for those, we call it the macroscopic traffic state estimation. And those information actually can formulate different sensing paradigm. For the ideal cases, which is we both have the local states and the global states, we call it global sensing. But in reality, in most of the road, we don't have the access to the global states, so we only have the local sensing paradigm. And under two different sensing paradigm, I designed two different control strategy, and the two control strategy actually has teacher and student relationship. So first of all, for the global sensing paradigm, I designed the kernel-based feedback control, which takes the all three states as the input and trying to output the smooth speed profile for the vehicle to execute. And the idea is that we use the kernel planning for target speed design and leave the gap regulation for the vehicle level. So this is actually a hierarchical control. As I mentioned before, not every road has the ability to provide the global sensing paradigm. Then what if we still want to achieve the similar smoothing effect? So that's why under the local sensing, I'm trying to use the imitation learning to get rid of the reliance of the traffic state estimation. And different from the usual usage of the imitation learning in autonomous driving research, here we utilize our kernel-based feedback control as the expert to imitate from, or here I call it as the teacher. And the student, which is the imitation learning control, trying to mimic the behavior of the kernel-based control so that even without the macroscopic traffic state estimation as the input, it can still achieve the similar smoothing effect. So to give you a even a more detailed understanding, the thing that we are doing here is we firstly obtain those orange dots here, which is the speed profile we collected from the highway. And as you can see, this is very sparse, and also the speed oscillate a lot. And we want to apply the control strategy on top of that based on different constraints of the input so that we can generate this smooth green curve here for the AV to execute. And we try to train and evaluate in simulation in two different cases. First of all is we build our own simulator on a single lane setting with recorded real-world stop-and-go trajectories, because we think in this way we can reflect the real traffic condition in a very high fidelity and macroscopic level. And here is a common tool that we use for the traffic flow analysis, which is a time-space diagram. To give you a little bit background explanation, the x-axis represents the time while the y-axis represents the position. And this plot is actually generated with 200 vehicles trajectory. So each of the lane here actually represents one vehicle trajectory. And the color represents the speed of the vehicle. So the more greenish represent the more higher speed. As you can see here, for example, one vehicle just travel here without any interruption, free flow, and then it's hit with the stop and go waves here. He has to slow down, so that's why you can see the slope over there. And in overall, it represents that here, if the color is in black or reddish, means that the vehicle actually entered the zone that it has to stop or slow down. So this plot actually showcases that with our a single lane simulator. It actually can represent a scenario of the a traffic jam. And we also train and tested on multi-lane setting using open source traffic simulator called Sumo. And the way we generate the stop and go waves here is another mechanism, which is we injected different imbalance inflow and outflow. So first of all, in the single lane setting, we tested 10 different scenarios, and 7 of them are the light or moderate congestion. As you can see, the speed plot over there, they're still have the stop and go waves amplified. And heavy congestion, 3 of them are really congested, as you can see on the left. And overall, for those 10 scenarios, for the global sensing, which is the kernel-based control, we can achieve overall like 16.57% energy saving. And with the local sensing, which is we don't have the traffic state estimation for imitation learning control, we can still match the relatively the same like level of energy saving, which is 14.5%. And I also want to give you like a more intuitive like sense. This plots on the top is the time space diagram, and on the bottom is the speed profile, like the speed plots. And on the left-hand side, we show that without any control, and in the middle is the kernel-based control strategy, and on the right-hand side is the imitation learning control strategy. All these plots is generated with 200 vehicles simulation, and only 4% of that are the vehicles that we can control. And as you can see here, so like both the kernel-based control and the imitation learning control actively mitigate like the black area over there, and to like see it more clearly, you can see this like speed plot. Without any control, the speed oscillation is actually amplified more and more, while like after like we apply the control, we effectively shrink the stop and go waves here. And for the multi-lane setting, as I said before, we try to play around with different like downstream speed limit and the inflow to generate the imbalance inflow and outflow scenario. And each of the plot actually represent different like inputs and generate a different scenario to test on. And in our training, we actually only pick those that have the traffic jams, so that like it allows the system to learn to match behaviors that dissipate waves as opposite to overfeeding to a certain speed. And this is the animation video we captured from the multi-lens simulator. As you can see, on the top is without any control, and on the bottom is with the control. With only just like those like red cars we have the ability to control on, we clearly see that the traffic flow is moving smoother comparing to the top one. Here I also want to show you some numerical results, but that's a lot of number. I really don't want you to like focus on those specific number, but just pay attention to the color. The more reddish represents the more percentage change from the baseline, and the more bluish represent the more like percentage change decreased from the baseline. So we mostly focus on two metrics, which is the energy efficiency as a proxy, and also the acceleration or the speed like change. And for both the kernel-based control and imitation learning control, we effectively increase the energy efficiency compared to the baseline, and we decrease the acceleration compared to the baseline. And this is all under the control of the outflow rate that we didn't change that too much, because the overall like idea is we want to improve the system efficiency without harming the performance. So those like results from the simulation gave us a lot of confidence, and we are like excited to deploy that into the real world experiments. And as I mentioned before, this is the like a national scale collaboration project called Circles, which is, I believe, the largest mixed autonomy traffic field experiments to date. And it includes several different institutes, like universities, and sponsored by a lot of like, sponsored by NSF, DOE, DOT, and a lot of other industry collaborators. And we deployed 100 partially automated vehicles on the I-24 highway, surrounded by the human commuters during the morning rush. And the reason we chose the I-24 highway is because thanks to Professor Denwerk from Vanderbilt, they have like a I-24 motion project on that like test bed, which is a 4-mile segments with over 200 high-resolution cameras. Those equipments provide us the ability to extract and monitor all the trajectories of the vehicles passing by so that we can effectively analyze how much improvement we can bring to the whole system. And the control framework we deployed in the experiment is very similar to the hierarchical control framework I introduced previously. So overall, it has a higher a layer we call speed planner, and equipped with the lower layer of the vehicle controller. The speed planner's objective is exactly what I mentioned before, trying to obtain and observe the information from the traffic state estimation and generate a smooth speed profile for the AV to execute. But that's lower level lower level control is handled by the lower controller to consider about the gap regulation and also the safety constraints. And so my main contribution is I integrated my previous control strategies into the speed planner layer so that it can provide valuable and effective speed for the vehicles to execute. So during this 100 automated vehicles test, is actually team efforts and coordination contains a lot of different elements. And my contribution mainly focused on, as I mentioned, design the core control algorithms and also support the energy modeling and evaluation, and deploy the controller on hardwares and cars and support the experiment logistics. And here, I want to utilize a typical day during the test week to showcase to you how this experiment is conducted. So usually we will need to arrive at the parking lot or the a headquarters where we parked all the 100 autonomous vehicles car at around 5 a.m. to conduct a gear check for all the drivers. And after we send off the first batch of the drivers, I need to go back to the headquarters and monitor the test and trying to detect some possible bugs for the algorithm. And after the morning experiments conclude, I need to refine and improve my control algorithms. And in the early afternoon, I will try to deploy the refined algorithm on a few test vehicles. And this usually goes several rounds, refine, redeploy, and retest. And in the late night, we will finally deploy the version that we fixed for the next day's test. And so after a week of the test, we collect a lot of data, and here I want to show you some numerical results. So in summary, we actually use less than 2% of automated vehicle penetration to achieve more than 10% measured system-wide energy savings. And here is a plot to show you the relationship between the fuel consumption with the distance of the human-driven vehicle that between our controlled automated vehicles. And it shows that the nearer the human-driven vehicles to the autonomous vehicles are, the more fuel efficiency they could gain, which align with our intuition. And besides that, we actually, thanks to the I-24 mission team, we generate the largest time-space diagram in the world, and it spans over 3 hours of the time of the 4 miles. And as you can see, each of the curve here represents one trajectory of the vehicle, and the white curve here is the 100 cars that we control. So in summary, for this project, I showcase you how I use a few automated agents to improve the system efficiency. And the specific problem we tackle on is the stop and go waves. And we're trying to use a few partially automated vehicles to dissipate those stop and go waves while maintaining the overall throughput that is not harming the original performance of the system. And the solution we propose here is using those autonomous vehicles as the robot managers to shepherd the human. And the research framework or the idea spans from the modeling to control to experimentation like loop, while for the modeling layer, we're trying to capture the traffic state estimation. And for the control layer, we observe those information to design the target speed. And for the experimentation layer, we use those, execute the plan to shepherd the human drivers behind it. And so like with this, we can like clearly see that the overall like the core thing is how we design those target speed. And after this project, I realized that if we want to obtain a really good like a target speed for the vehicles to execute, besides a good control, we really need to obtain a good like traffic state estimation, which is like corresponds to how good we understand the traffic and how good we understand the dynamics of the systems. So that actually leads me to another line of my research. And today, due to the time constraint, I will just give you a really brief highlight of that. Is I designed a physics-informed neural solver for hyperbolic partial differential equations. So why hyperbolic partial differential equations is actually like the traffic flow can be modeled by the hyperbolic PDEs. And this solver actually can provide us with a more accurate, robust, and computationally efficient tool for traffic state estimation. And different from like previous like physics-informed machine learning approach, which is just adding the PDE into the loss to train, for this method, we specifically build on the finite volume method, the numerical method itself, but we replace the analytical numerical flux by a neural network, which enable the whole whole framework to be more flexible and also more robust. The key contribution of this approach, we call it neural finite volume method, contains, first of all, in terms of accuracy, it outperforms all the known finite volume numerical schemes across multiple hyperbolic PDE models. And it is also robust. It outperforms numerical baselines on multiple noisy traffic field data. It's not just like synthetic PDE data. Besides that, it's also computationally efficient. It matches the computational cost of first order finite volume scheme. So in summary, it's actually, besides a neural solver, it gave us a tool to support the simulation and control design. As I mentioned before, we collected a bunch of data from the experiments that we conducted, and those data right now, closed loop can help me to verify and refine my modeling method here. And we deployed the NFVM method on this I-24 motion data set, which contains 10 days of traffic data, which is over 600,000 of vehicle trajectories. And we actually just trained NFVM on the first hour of the data, which is only 2.5% of the data set as the training set. And we firstly validate that on the traffic prediction task on the same day. And in the middle is the prediction results that generated from our NVM method. And on the right-hand side is a classical baseline numerical schemes, which is good enough to conduct the same task. And as you can see, our method outperformed the baseline clearly in terms of predicting the right direction of the free flow, and also in terms of capturing the dissipation of the stub angle waves. Besides that, we also try to just apply the current model to all those other unseen days, and it's surprisingly robust. And even for those totally different traffic scenarios, it can accurately capture the shape and the dissipation and the free flow speed of the traffic. So moving forward, I'm really excited to firstly combine the two lines of my research, trying to see how much I can improve by combining my current neural finite volume method with my control strategy to see how much in terms of I improve the traffic state estimation, then it can improve the overall control performance. And besides that, the modeling solver that I developed is not just restricted to the traffic flow systems. It can definitely apply to higher order hyperbolic PDEs. For example, some ocean wave systems, and also shockwave that trail a supersonic jet. And moreover, I'm also interested in discovering more control strategies in different mixed autonomous systems, not just restricted to the ground transportation as I showcase here, using a few automated vehicles to influence the other human-driven vehicles, but we can naturally expand that into other mixed autonomous systems. For example, the drone systems contains both autonomous and piloted drones, and also the emerging advanced air mobility systems, including the unpiloted and piloted air taxis. So I'm very excited about the future lens, and thank you so much for listening to my research talk today. Thank you.